All right, now we're going to talk about Chapter 4, Section 5, which is integration by substitution. So we're going to start off by talking about pattern recognition. Anti-differentiation of a composite function. So if g is a function whose range is an interval I, and f is a function that is continuous on that interval, if g is differentiable on its domain, and capital F is an antiderivative of lowercase f, then the antiderivative of f of g of x times g prime of x dx equals capital F of g of x plus c. Basically, we're saying if I can replace something in the function with u, and I take the derivative of that thing, call it du, if I can find both of those in the function, I just take the antiderivative of f of u plus c. So let's try it. To find this antiderivative, it looks pretty wonky. I could multiply it all out and figure it out that way. Or I could say, well, this kind of looks like it could be something squared. So if I called u x squared plus 1, well, the derivative of u would be 2x, du dx is 2x. But we're actually going to write it as du equals 2x dx. If I can find 2x dx in this equation or this problem, I can substitute in a du. So I have rewritten this as the antiderivative of u squared du. Now that's a whole bunch easier because I know that I just make it u cubed over 3 plus c. But you have to take one more step because we don't want a u in our final answer. U is actually x squared plus 1. So we're going to make it x squared plus 1 cubed over 3 plus c. And there's our answer. Much easier than multiplying all of this out. And sometimes we need to do this. The cosine of, 5 times the cosine of 5x dx, antiderivative. If I make u the inside piece, which is 5x, I can say du is the derivative of 5x is 5, and then we stick the dx over there. For anti-differentiation, we split apart the du and the dx. I have 5 dx. So I'm taking the antiderivative of the cosine of u du. Well, the antiderivative of cosine is negative, positive sine of u plus c. Well, instead of u, I need to go back to 5x. And my antiderivative is sine of 5x plus c. So let's do a couple more examples. In this first one, I would say that u is x squared plus 1. And du then is 2x dx. So I'm finding the antiderivative of u to the 4th power du, which is u to the 5th power over 5 plus c, which is x squared plus 1 to the 5th power over 5 plus c. For the next one, I would say u is x cubed plus 1. Then du is 3x squared dx. Oh, look at that. It's perfectly in there. We're finding the antiderivative of u to the 1/2 power du. Well, that makes u to the 3/2 power divided by 3/2 plus c. So I have 2/3 x cubed plus 1 to the 3/2 power plus c. And then this last one, if I make u equal to tangent of x plus 3, then du is secant squared of x dx. So I'm finding the antiderivative of u du, which is u squared over 2 plus c, which is actually the tangent of x plus 3 squared over 2 plus c. All right, now we're getting a little crazier because our actual du is not always in the problem. So we have to get a little creative. This is very similar to one of the last problems. We made u equal to x cubed plus 1. which meant du was 3x squared dx. The problem here is that I just have an x squared dx. I need to get that 3 out of there. So I have 1/3 du equals x squared dx. So to take out the x squared dx, I need to put in a 1/3 du. So I'm taking the antiderivative of u to the 1/2 power times 1/3 du. The only difference is that I have an extra constant in there. So I'm going to have u to the 3/2 power divided by 3/2 times 1/3 plus c. And that makes 2/9. Instead of u, I'll switch it back to x cubed plus 1 to the 3/2 power plus c. Next one will be very similar. Our u will be x squared plus 1, which means du is 2x plus dx, sorry. Well, I don't have a 2x dx, I just have an x dx. So I divide that 2 out of there. 1/2 du is equal to x dx. So I'm finding the antiderivative of u to the 4th power times 1/2 du. Same thing as before, it becomes u to the 5th power over 5 times 1/2 plus c. Well, instead of u, I'm going to switch it back to x squared plus 1 to the 5th power. Now it's over 10 plus c. And over here, if u again is tangent of x plus 3, then du is secant squared of x dx. Notice that we just have an extra 2 hanging out. This time it's just extra stuff. We have 2 times u du. Well, that becomes u squared over 2. The 2's cancel. We just have u squared plus c, which is tangent of x plus 3 squared plus c. Integration has the constant multiple rule. If I have a constant times a function inside my integral, I can take that constant out front. Just remember that that's always an option. Now let's find a definite integral. We start with finding a u substitution. I could take out x squared plus 1. And then my du would be 2x dx. Well, I don't have a 2x, I just have an x dx, so we divide that 2 over. 1/2 du is equal to x dx. Now the constant multiple rule says that when I plug that back in, I can take that 1/2 out front, antiderivative of u squared du. So I could say 1/2 times u cubed over 3 plus c, or 1/6 times x squared plus 1 cubed plus c. We call this a change of variables. So in a change of variables, we take and we say, okay, well, this inner piece here, that's going to be u. G prime of x dx, that is our du. So we are actually finding the antiderivative of f of u du, which is capital F of u plus c. This problem looks like it could be quite complicated until we create a u substitution. If u is the complicated part, 2x minus 1, then du is 2 dx. So that means 1/2 du is dx, because I don't have a 2 just hanging out in my problem. So I'm going to take the antiderivative of u to the 1/2 power du, but I need to account for that 1/2, so I'll stick it out front. So I have 1/2 times u to the 3/2 power divided by 3/2 plus c, which makes 1/3 u to the 3/2 power plus c. But we have to always remember to switch it back. Don't leave the u in your problem unless you had a u originally. So I have 1/3 of 2x minus 1 to the 3/2 power plus c. All right, this time we have to get a little crazy, it looks like. So to get crazy on this one, u looks like it would be 2x minus 1, which means du would be 2 dx. We don't have a 2 anywhere, so 1/2 du would equal dx. That gives us 2 x times the square root of u times 1/2 du. We still have an x in there. We can take our du though and rewrite it, or sorry, our u, and rewrite it as an x. I add the 1 over, so u plus 1 equals 2x. Divide the 2, u plus 1 over 2 equals x. So we have u plus 1 over 2 times u to the 1/2 power times 1/2 du. Now it doesn't look that much simpler, right? I just kind of changed where the adding and multiplying type of stuff was. But we can actually combine this a little easier than this, and we can find this antiderivative easier. So I would distribute my u to the 1/2 in, which makes u to the 3/2 power plus u to the 1/2 power over 4 du. And then I can make it u to the 3/2 power over 4 plus u to the 1/2 power over 4 du. And now I can actually find my antiderivative. U to the 3/2 power, I add 1, making it 5/2. Still over 4, but I divide by 5/2. Plus u to the 3/2 power, still over 4, but I divide by 3/2, plus c. 4 times 5/2 is 10. So I'll replace my u back with 2x minus 1 to the 5/2 power over 10 plus 2x minus 1 to the 3/2 power over 6 plus c. All right, we got our antiderivative. Sine squared of 3x times cosine of 3x dx. Well, I can say, all right, well, u is 3x and du is 3 dx, which means 1/3 du is dx. Okay, so I've rewritten it as sine squared of u times cosine of u du with a 1/3 out front. That still didn't quite help me. But I can actually do it again. Let's say that v is sine of u. That means dv is cosine of u du. Now I can rewrite this as 1/3 the antiderivative of v squared dv. And I can keep going, 1/3 of v cubed over 3 plus c. Now I just start plugging stuff back in. V was sine cubed of u. Now it's over 9 plus c. And u was 3x, so I have the sine cubed of 3x over 9 plus c as my antiderivative. So some guidelines here. Choose a substitution, u equals g of x. Usually it's best to choose the inner part of a composite function, such as a quantity raised to a power. Compute du equals g prime of x dx. Rewrite the integral in terms of u. Find the resulting integral in terms of u. Replace u with g of x to get an antiderivative in terms of x, and check your answer by differentiating. And now we have the general power rule for integration. G is a differentiable function of x. The antiderivative of g of x to the n power times g prime of x dx is g of x to the n plus 1 power over n plus 1 plus c. Equivalently, if u is g of x, u to the n power du is equal to u to the n plus 1 power over n plus 1 plus c. That's really what we were just doing. It's recognizing the inner function in here. So think we'll actually pause this video here and take it up in the next one.